Hello, class. Hello, class. Today we are going to explore the relationship between the different gas variables. There are two options for this assignment. If you picked option one, you are currently watching this video demo, and I'm going to work through the PhET simulation. And your job is to complete the graphic organizer below. That kind of organizes all of the main ideas behind this simulation. If you chose option two, you do not need to watch this video, but you can always refer back to it if you need to. So before we begin, scientists in the late 1800s noted relationships between many of the state variables related to the gases. Those variables are pressure, volume, and temperature. And they also noted that relationship that they had with the number of gas particles in the sample being studied. Since there were so many variables, they knew that it was easier to study those relationships if they only varied two parameters at a time, or two variables, and held the others constant, or they were said to be fixed. And we're going to go through and explore each of these relationships. Now, there are names for the four different relationships. I'm going to refer to them today. There's Gay-Lussac's law, there's Boyle's law, Charles' law, and Avogadro's law. Okay, so your job as you are going through this video is to pay attention and fill out the graphic organizer. When it says variables tested, bold the appropriate ones when we are discussing that particular law. Same for variables kept constant. You can bold the particular ones that need to be kept constant. And then briefly describe what you're observing as we go throughout this video. It's good to take some notes on the behavior of the particles. And then for proportionality, that refers to the type of relationship. A pair of variables is directly proportional, has a direct relationship when they vary in the same way. One increases, the other also increases. It's an inverse proportional relationship. They vary in opposite ways. One increases and the other decreases. So keep that in mind as we're working through. On to the PhET simulation. If you click the link, it'll take you to the gas properties PhET simulation. Click the play button. And there are many options here. We're going to look at the ideal gas laws tab. Okay. The default has us holding nothing constant. We're going to start off by holding volume constant. We're also going to hold the number of moles of gas constant. The way I'm going to do that is by only giving one single pump of gas particles into my container. So this is a good representation of Gay-Lussac's law. We're going to be studying the effect that pressure and temperature have on each other when volume and moles of gas are held constant. So I'm going to go through one pump. You'll notice that there is no pressure reading at first. I'm going to go through and do that again. So notice it says 0. Even after the first initial pump, you don't get a pressure reading until that first collision that some of those particles have with the walls of the container. Keep in mind that pressure is defined as the forces due to the collisions particles have with the walls of container, not the forces due to collisions with each other. All right. Now you'll notice that the pressure is fluctuating. It's never going to truly stabilize due to the size of this container, but it is going to be somewhere in the realm of 5.8 to 6.0 atmospheres. So if you are doing the simulation on your own, you're welcome to estimate that. I would say this is about 6.0 atmospheres, and the temperature is 300 Kelvin. I'm going to apply heat, and I'm going to double my temperature. And so I'm going to, went a little too far. Let's take it down to about 600. All right, doesn't have to be exact, but just enough to get an idea. Now, our initial values were 300 Kelvin and around 6 atmospheres. What do you notice about the values now? The values now represent a pressure of about 12 atmospheres, which is double that of the initial pressure, and we also doubled our temperature. This is a direct relationship. So when the temperature increases, the pressure will also increase. Now, if we pay attention to the particles themselves, you see that they're moving much faster than they were at 300 Kelvin. What we've done by applying heat is we've increased the average kinetic energy of our particles, so that way they are moving faster. When they're moving faster, they're going to have more frequent and more forceful collisions with the sides of our container. Therefore, the pressure will go up. Let's take a look at what happens when I cool it down to about half of 300 Kelvin. All right, so we're around 150 here. This is about half of my original temperature and pressure, which was 300 Kelvin and 6 atmospheres. You'll see that the pressure is hovering about 3.0 atmospheres. So this is a direct relationship. It is proportional. Keep that in mind when we're talking the Kelvin scale. Kelvin scale is a measure of the average kinetic energy of a sample, and that it is directly proportional to the amount of motion occurring. And that makes sense with what we're seeing. I could continue cooling this down. Another vocabulary term we talked about was absolute zero. So I wanted to get it all the way down to zero, and this one takes a little bit longer if you're doing the simulation on your own, and that is okay. Patience here. But you'll notice the particles are slowing down, and the pressure is decreasing because there are very few, if any, collisions with the walls of our container. Now the pressure meter is reading 0. And we are officially at 0 Kelvin. Now, I take issue with this simulation because at 0 Kelvin, we theoretically should have no motion of our particles. When you look, you can still see some slight motion, but it is very, very minor. We have very little motion at 0 Kelvin. We also don't have any collisions with the sides of our walls. Okay, so to recap, Gay-Lussac's law, we tested the temperature and pressure relationship. We kept constant volume and moles of gas, and this is a direct relationship. The next one we're going to look at is the relationship between pressure and volume. So I'm going to do a single pump here, and once I have that single pump, you can see the temperature box opens up. I'm going to keep temperature constant, and I also only have one single pump of gas molecules in there, so I'm holding the moles of gas constant. We're at the same initial pressure and temperature as we did before. I want to see what happens to my pressure if I take the container down by about half its current size. I'm going to decrease the volume from here. That's about halfway. All right, it's not perfectly half, but if I went in a little bit more, I'd be just about there. Half the size of my original container, the pressure has now doubled. That's an interesting relationship. So I decreased the volume by half, and the pressure doubled from its initial point. Now, if I go back again to around that starting point of 6.0, what happens if I expand the container? When I increase the volume, the pressure decreased. When we think about this for a minute, it makes sense. Pressure is due to collisions with the walls of the container. In a larger container, there's going to be more space for the particles to move, and therefore fewer collisions with the walls of the container. When I have a smaller volume, there's less space for the gas particles to move. They are more compressed. Therefore, there are going to be more frequent collisions and a higher pressure. All right, let's reset. As we're resetting, this is a pressure and volume relationship we just tested for Boyle's law. Sorry, I should have mentioned the name. And moles of gas and temperature were constant. Again, pressure and volume were tested, temperature and moles were constant. This is an inverse relationship. When one went up, the other went down. All right, next one we're going to test is Charles' law. So we are holding the pressure constant here. We're holding pressure constant so that way we can measure the effect that temperature and volume have on each other. So as I heat up my sample, you'll notice the volume also increased. Part of the reason this is happening is due to the gas samples gaining more energy, and therefore more speed. By having more speed, they are going to have more frequent collisions with the sides of the wall, and because it's a flexible container, it causes that container to expand. And I just got this lovely error message. Pressure cannot be held constant because the volume's too large. I didn't intend to do that, but it is a good thing to talk about. Think about a balloon. If you have gas in a balloon and let that balloon expand, at a certain point, there are limits to every flexible container, and that balloon will pop. And that's essentially what happened to me. All right, well, what happens if I cool it down? Well, if I cool it down, it allowed the gas particles to get closer together because they had less energy, and so they become a little bit more compressed. So the volume of the container will shrink to accommodate the less size that the particles need to spread out. So as I cool my substance and decrease temperature, the volume will also decrease. As I increase temperature, my volume will increase. So this is Charles' law. We just tested volume and temperature. Pressure and moles of gas were held constant, and this is a direct relationship. All right, the very last one we're going to look at is Avogadro's law, looking at the number of moles of gas and its relationship to volume. So this one's tricky here. When I look at my initial sample, again, I'm keeping my temperature constant, my pressure constant. As I pump more gas into here, I'm sorry, I checked the wrong box. Let's try that again. Here's my initial sample. Temperature is held constant, pressure is held constant. All right. So I could try and remove some gas particles in here. And as I remove gas particles, you saw that the container shrinks. So there seems to be a relationship where the moles decrease, the volume decreases. What happens if I add more gas? Oh, I didn't even need to add all that much. But as I add a little bit more gas, it causes the volume to expand. Those gas particles are all at the same average kinetic energy and at the same pressure. So since they're colliding with the same frequency and with the same force, the only option for the container to do in response to the addition of more gas is to expand to accommodate it. So we have more collisions, or not more collisions, but the collisions cause the container to expand as a result of keeping pressure and temperature constant. And this last one I don't know if I mentioned, but the name is Avogadro's law. There's a relationship between volume and moles of gas, which is essentially just the amount of particles that we have. Temperature and pressure is constant. This is also a direct relationship. In our next lesson, we are going to spend some more time with these simple gas law relationships, and I'll show you how to quantify some of these things in addition to learning more about gas behavior through kinetic molecular theory. We're also going to look at unit conversions and prepare for some more time with the ideal gas law.